which requires job scheduling. And if any disruption or failure of the machine tool in between the schedule occurs, there is disruption of entire production resulting in rescheduling and chaos. That is where digital twins play a big role. So most people don't fully appreciate why digital twins exist because they completely rely still on periodic maintenance, reactive maintenance, and monitoring based on supervisory control and data acquisition system, which has complete limitations on predictability and zero level system intelligence. So can we predict a failure before it happens? So instead of doing that, we are just monitoring the machines. We don't understand them. So that is where digital twin play a great role. To simply put it in simple words, digital twin is a real-time virtual replica of a physical system, but it is not static. It continuously updates using sensor data to monitor, analyze, and predict the system behavior. Now, let me clarify something very important. Digital twin is not just a CAD model or a simulation or a static representation. It is alive. It gets data in real time. It evolves continuously, and it is in predictive nature, not just a static model, like a simulation or a CAD file. So in simple terms, we understood what digital twin is really is. But the next question is why this concept has becoming so important now. To understand this, we need to look at how industry itself has been evolving over the time. For example, industry 1.0, where we have basic mechanization using steam power and so on. If you move on to industry 2.0, mass production, including electricity, assembly lines, and so on. In industry 3.0, where we use automation using PLC controls and computers and electronics. Now we are in industry 4.0, where we see a cyber physical system with IoT, interlinked physical systems connected through wireless network or internet. But this only brings connectivity through IoT. But digital twins add something new, that is intelligence. IoT collects the data only, but the digital twins helps us to understand the data and convert it into tangible actions. This is most important, where the shift is coming from. So from a reactive system, we are going to a predictive and intelligent system. And moving on to industry 4.0, the focus 5.0, the focus is on intelligent, adaptive, and human-centric systems. This is exactly where digital twin fits. So we are moving from just collecting data or connecting different physical systems over network, then adding intelligence to them to make their own decisions. So we are transforming from mass production to mass customization and moving from reactive to predictive operations with intelligence. So let me here explain briefly how its digital twin works in simple terms. Let us take a physical example. For example, a turbine as shown in this figure. The sensors, there might be various sensors sitting on there, collecting real-time data such as vibrations, temperature, speed of the turbine, and so on. This data is usually sent to a digital replica or a virtual model of the turbine, and the model updates and behaves exactly like a real system. Now, using this model, we can monitor the performance, predict the failure, and also test what happens, what if scenarios, which are not physically possible. We cannot test the turbine for what if scenarios because it's very costly, right? So in those what if scenarios can also be simulated. So this is not just a model. This is living dynamic system. So in order just to summarize, digital twin is not just a technology. It represents a shift from reacting to failures to predicting and preventing them. And this is why it is becoming a key component in modern mechanical engineering system. And to simply answer why this technology is needed, in mechanical engineering perspective, there are four fundamental advantages. They are minimizing the downtime of a machine system, improving efficiency, enhancing the maintenance required, and taking better decisions to improve the productivity. Now that we understood what a digital twins is in simple terms, the next important question would be where it is actually used in industries. This slide presents the digital transformation of industries using digital twin. Now, digital transformation is the key enabler for various business cases of future factories. For example, take smart manufacturing. Digital twin enables advanced automation, AI-driven adaptive control, real-time data analytics, reduced lead time, which makes the system adaptive, self-improving, and decision-making. Coming to predictive maintenance, the major advantages include conditional monitoring, failure prediction in advance, optimized schedule, improved downtime. Uptime. That is reduced downtime and increased uptime. That is utilization or throughput of the machine is increased. Coming to supply chain optimization. A transparent forecast can be visualized. That is, assume the supply chain of an Amazon store. It delivers to millions of customers and they don't have warehouses everywhere. Only hubs are there. Assume such kind of supply chain is optimized using a digital twin. It can also make faster response to market uncertainties, improve accuracy, and predict the demand over a period. So the decisions become more data-driven and also accurate. Coming to the workforce enhancement. So there is a what you call a misunderstanding of that if digital or AI takes over, there will be no workforce at all. So this is a clarification. So digital twins enable enhanced safety to the workforce. There will help for generation of co-robots, that is collaborative robots, helping to reduce the stress and strain taken by the workforce, remote assistance to operate remotely the machines. And if the physics of the entire system is not known, then data-driven training can also be done, which enhances both productivity and safety. So if you observe closely, digital twin is not just improving the machines, it is transforming the entire industrial ecosystem. So you can say that digital twin is the backbone of industry 4.0 and 5.0. Now, as that we understood where a digital twin is applied over across industries, now the question is how fast this technology is actually growing. So these are the key areas where digital twin is really being actually utilized. The four fundamental, I mean, not limited to them, but from mechanical engineering systems perspective, these are the major categories. That is mechanical, computer-aided engineering, finite element analysis, product life cycle management, and digital thread. That means handling the data, industrial IoT and sensor integration, and AI-driven process twin. So digital twin is not a simple tool. It is an integration of simulation, data, intelligence together. These are the global twin adaptation predictions over a period of 5 years, sourced from various resources. Okay, the highest adoption is expected in predictive maintenance. Currently, it is approximately about 45% and projected to increase up to 90%. Then comes autonomous twin self-optimization, real-time prediction of remaining useful life of a product, virtual commissioning, that is deployment of digital twin to analyze the entire cost of project and reducing capital cost or capital expenditure. dynamic product design and FEA, that is continuous optimization of a model, supply chain optimization, as I explained, the example of Amazon, and a digital twin as a service. So most small firms cannot afford large computational systems that are required for them to handle these small twins. So the cloud system or cloud digital twins can be helpful to virtually develop their framework to enable the system to predict whatever they are required, not from the scratch. So that is a digital twin as a service. Autonomous intra-plant logistics, similar to supply chain management. Connected global, connected golden batch analysis. It is like benchmarking various same processes over global square. Global production network twin, handling the network between various connected intelligence systems. Local shop floor twin. This represents a digital replica of the entire shop floor of a machining or production system. Big data driven quality optimization, talking about improving the quality of products producing using data analytics. Vibration wear life twin, that talks about wear and tear of different physical things. And the last parts are production process visualization or process twin. Then comes the system level twin, that is smart factory. The complete factory is represented in digital form. Even though the expected share of the current implementation of digital twin in the bottom areas are very low, you can see the projected scope of implementation is rapidly increasing. That is more than 50%. So this clearly shows that digital twin is not experimental anymore. It is becoming and has been becoming the mainstream. So digital twin is becoming a standard tool in design, a necessity in maintenance, and also the core component of smart manufacturing. Now let us understand the core components that makes a digital twin functional, the foundational core components. So in the foundation, we have the physical system. This could be anything like a robot, a turbine, an engine, a CNC machine, everything which works on the physical grounds. Then they are connected using network of sensors, IoT sensors, which measure mechanical signals such as temperature, vibration, pressure, speed, humidity, etc. And they send this data to digital model. So this data transmission is not direct. So data acquisition systems usually collect this data and make them suitable, because digital models only understand zeros and ones. But sensors data, if it is not analog, if it is analog, we get physical signals that need to be converted and pre-processed before we transmit it to the digital model. So the digital model is the most crucial part of the digital twin. This is where we create a virtual representation of the physical system, which may be a physics-based model like FEA, CFD, and so on, or a data-driven model if the physics of the process is yet to be understood. This model tries to replicate how the real system behaves. Then on top of this, we apply analytics and AI to detect anomalies, predict failure, and optimize the performance. The output of these analytics and AI will be fed back to the physical system to make necessary changes. So this is where intelligence is added to the system, the analytics, the application tools, the machine learning, and so on. So simply speaking, integration of all these components enable a functional digital twin. Now, as that you understood that what are the core components, Let us understand the level of digital representation of a system, because there was a confusion always with the people. So the first level of digital representation is the just digital model. It might be a CAD model, simulation model. Even though we are trying to predict something, analyze stress or analyze force, system behavior, frequency response analysis, still we don't have real-time data integration with the physical system. So the system is just a static model. It is not updating, neither evolving. So we cannot take this as a digital twin. The second level of digital representation of a system is called digital shadow. Digital shadow, where the data, we have a reliable digital model that reflects a physical system, and we have an integration of physical system with the digital model. That is one way data flow into the digital model. But if you need to transmit your analysis from the digital model, you have to transmit use manually. There is no bi-directional flow of data in digital shadow. Then third level of representation, that is digital twin, where you can see there is bi-direction flow of data. That is, there is a viable digital model which completely represents or high fidelity represents the physical system, which has the information flowing from the physical system, and the feedback and control signal going to the, feedback and control going from the digital model to the physical system. So it is, simply speaking, a bidirectional data flow predictive and intelligent system. That is physical system sending the data, and the data from the data sent to the digital system is analyzed and sent back to the physical system as control. So this enables real-time monitoring, prediction, and optimization. So now that you understood the working scenario, various levels of representation, and the core components of a digital twin, let us organize them into a structure that is called digital twin architecture. So usually, according to the ISS standards, usually a digital twin consists of 5-layer architecture. That is physical layer, starting with the bottommost physical layer, going to communication layer, data layer, model layer, and application layer. There is data upstream, and the downstream is actuation signal. So we are getting the real-time decisions and control signals coming from the application layer, model, transmit to application, and they are downstream to the physical layer. So let us start with the physical layer. This is the foundation of entire system. This is the real world system, the actual mechanical asset we are operating. From engineering perspective, here we define what to measure actually. Why? What are we trying to do? So we have two important elements here. They are sensors, which acts like inputs. They capture various mechanical uh, signals like vibrations, strains, temperature, operating conditions, and so on. Then the other important part of this physical layer is actuators, which act like an outputs, which receive the control commands from the digital twin and make them as a tangible actions. So this layer usually represents the reality, the ground truth, or the source of the truth of the digital twin. Even so, whatever we model, whatever the data is sent, whatever it is analyzed, whatever intelligent decisions it is making, but if the actuation or the entire mechanical action in the physical layer is not useful, then the digital twin also represents garbage in, garbage out. Then comes the communication layer. This layer connects the physical system to the digital world, where we have industrial IoT. That is an integrated network of sensors, physical assets, and communication protocols, where The real-time data from sensors is processed by gateways to either edge computing or cloud computing. This might sound really technical. So let me put it in a simple fashion. The protocols are like a systematic set of instructions to send data from one machine to other machine such that they understand each other. And the main challenge here is how to transfer this data efficiently, securely, and in real time. So we use these gateways to convert these industrial signals into useful formats using communication protocols like MQTT or OPC-UA. They are like abbreviated for machine queuing, telemetry, and open platform communication unified architecture. Different communication protocols to suit different applications. For example, MQTT is lightweight. It can be used to transmit data from small IoT sensors to cloud, while OPC UA is structured and useful for communicating between industrial PLCs. So these send the data out. Then it depends on where we need to process this data. So sometimes the application requires real-time control, fast control sitting next to the system. So that is where we talk about edge computing. Edge computing, the process happens near the machine. While cloud computing talks about transmitting the data to cloud, store them, and use it for long-term analysis. So we use cloud infrastructure for that. Now that we understood that how data is transmitted, then the next question is what happens to this data once it is received? So this is handled by data layer. So in mechanical systems, we are not dealing just with one type of data. We have multimodal data like sensors data, thermal images, image processing, operational signals, whatnot, all synchronized with timestamp. So this data is obviously directly not useful. We need to perform pre-processing because most of the electronic signals we use noise removal, timestamping, data normalization. That is, if we have any uh, redundancy in the data, that has to be removed. So after pre-processing the data, then there is another process called synchronization. That is, in mechanical systems, different sensors operate at very different sampling rate. That means the number of samples corrected by each device may not be the same. Suppose thermal camera captures images, maybe say 10 images in a minute, while vibration sensor senses the signal at high frequency, maybe 20,000 observations per second or 10,000 observations per second, which is way beyond, which is way higher than the image processing data. So these synchronization helps to convert these raw signals into reliable structured information where the data is stored in time series data, timestamp, and this data is further processed by cleaning. So this is where the some of the outliers, that is missing points or sudden abrupt changes that should not be in the sensor data had to be handled, without which the data would not be accurate enough. As I told earlier, if we don't have accurate data, then the digital twin will also output garbage. So the data quality plays a big role. So how clean and sophisticated is your data, the better accuracy your digital twin can predict. So after all this process, the result is clean, time-stamped, structured data ready for modeling and analysis. Now that we have understood how the data is processed, how the data is stored and processed. The next layer, that is model layer, acts like a core intelligence of a digital twin. This is where system understanding resides. This is actually the brain of the digital twin. From engineering perspective or mechanical engineering perspective, this layer represents the convergence of traditional mechanical engineering and modern data science. The inputs include clean time series data, calibrated thermal maps, operational state data, and so on. So there are two types of models. That is physics-based models. These are foundational of any reliable digital twin. We use sophisticated engineering models such as finite element analysis, computational fluid dynamics, or multi-body dynamics. These help to understand various things, like why the system behaves the way it does. However, however, these models are computationally expensive. Right? You can't imagine you are running a CNC machine and there is an anomaly detected. You can't run the entire FE simulation sitting there, which consumes 10 hours to predict something. Right. So in those conditions, you need to reduce the order of these models. So that is called reduced order modeling, or also called model surrogates. These are uh, reduced mathematical forms of analysis representing the same systematic behavior that is understood from a complex FE analysis. For you to understand clearly, sorry, for you to understand clearly, let me make a good example here. I assume most of you are experienced with chatter vibrations in machining. So in order to solve the dynamic behavior of this chatter vibration in machine tools, the mathematical representation of the dynamic scenario includes delayed differential equations. So in reality, to solve these delayed differential equations, because they cannot be simplified and cannot be solved directly because they are interrelated, and there is a time delay associated with the differential equation. So their variables cannot be separated easily to analyze them. So in those conditions, a reduced order or a surrogate model like zero order solution could predict the chatter stability loss. That is, it could predict the cutting conditions where chatter vibration might not occur within few seconds. Instead of solving the delayed differential equations, the complex delayed differential equation systematically. To solve them systematically, you need discrete time domain analysis in real time. So that is not feasible in real situations. So that is where this reduced order modeling comes into picture. It simplifies complex situations into simple mathematical models so that the result can be obtained in seconds. Now, in addition to the physics-based modelings, when the physics of the system is not completely understood, we use machine learning models. That is, the models are driven, and the models are data driven, and they help to understand different patterns, predict failures, detect underlying relationship between inputs and outputs, and so on. For example, let us take an example of a bearing in a spindle. So if you really model that in FE, you might not understand the relationship between the vibration outputs, the vibrations measured on the spindle, to really the interlink between the life of the bearing. So this is where the machine learning models try to correlate them, the input and the output. So this is highly useful where we cannot describe the system by physics alone. So pattern recognition, anomaly detection is the primary role of the machine learning application in digital twin. So let us understand few basic various ML methods. Not in detail, just a glimpse. Deep learning. Deep learning is like exactly can be mimicked to our human brain, which can process some nonlinear data. So it is exceptionally good in handling unstructured data. So structured data is like we are labeling the data like this is text, this is a table, this is graph, this is image, and we feed into the system. That is called supervised learning. We are labeling and we are giving similar type of input to the machine learning model where it understands and predicts. While in deep learning, we have unstructured data like thermal images and complex sound patterns and so on, which can be processed. Then unsupervised learning is like finding hidden patterns, like anomaly detections, where the data is not labeled. Then there is one more thing called reinforcement learning. That is learning by trial and error. And once we achieve the target, we give rewards. And we train the system to get higher reward as we go towards the target we specify. Like example, adaptive reinforced control optimization. Then comes the real trend in digital twin research, that is hybrid approach. The most powerful digital twin today is hybrid approach. They combine physics based understanding with data driven intelligence. This allows us to understand both why is this happening and what will happen next. We can enjoy the benefits of both the worlds. So this is why we call this model layer as heart of the digital twin. Because without this layer, the system can only monitor but cannot think. Now that we have developed intelligence in the model layer, we need to apply it somewhere. That is where application layer comes into picture. So how do we actually use these predictions or insights that are developed by the digital model? The application layer is an interface between the digital model and the real physical layer, which usually predicts remaining useful life, failure predictions, what if simulations, alerts, alarms, and so on. These are not raw data anymore. These are interpreted or intellectual insights. The main role of this application layer is to convert these intellectual insights into tangible or actionable decisions. In simple terms, it transforms analysis into action. There are various things that go in between this action layer, application layer. They are first we have this decision support system. These systems combine model predictions, historical trends, engineering constraints to recommend the optimal actions. For example, scheduled maintenance before the failure occurs. Then comes visualization system, where we are trying to visualize the digital system and its performance. Real-time dashboards explaining the parameters you are looking into, like speed, temperature, vibrations, and so on. So you also can see the digital virtual representation of entire system, performance charts, indicator. It is like a visual dashboard to understand the entire system performance. This allows the engineers to monitor the entire system in real time. Then comes the control interface. The application layer also connects to the control systems. So we have these PLCs, programmable logic controls, distributed control system that gives control signals that are required to give tangible actions to the physical system. So these systems, these enable the system to execute whatever decisions we are taken automatically without human intervention in advanced systems. Then the important aspect of application layer is the closed loop integration. This is the most powerful concept without which we time feedback and real time monitoring. That is both data coming from physical system and control action going simultaneously, and understanding whether we have any an error or a deviation from the desired output. So now that we understood how a digital twin is built, the next important question is at what level we can apply a digital twin. So obviously, someone cannot start a uh, complex discrete system level twin that is on a global scale, on a full level factory scale. So these in mechanical engineering perspective, digital twins can be commonly classified based on scale and complexity. So as the complexity increases, the number of the data, the computation required and accuracy and the value of the digital twin also increases. So let us start with component level, the first level. So this is also called functional level. We are only targeting single parts or components of a system. For example, bearing of a monitor, a turbine blade, or something like that. It monitors parameters such as stress, fatigue, wear, degradation, and so on. So here we focus deeply on understanding only on single component and predict its remaining use life, failure, and so on. Then comes unit twin. That is, this represents a combination of sub-assemblies of individual components, like a spindle system in CNC machine. Then we try to predict its interaction between surroundings and its own mechanical and thermal behavior, and so on. Then comes asset twin. Asset twin is the next level. It's sometimes also called as product twin, which represents multiple components working together and their multiple interactions also. So the key function here is to understand how different components interact with each other and the overall physical performance. For example, CNC machine. So it is not just an individual part, but the system behavior at the machine level. Then comes process twin, next further level. This includes multiple assets working together. For example, production line, a power plant, and so on. The focus shifts from just understanding the interactions to synchronization, improving the throughput, optimization, understanding bottlenecks, and how to avoid them. Here we are optimizing how different machines are working together to improve a process. Then comes the final highest level, that is discrete or a complex system twin. This involves large scale system with thousands of interconnected elements, such as an aircraft like Boeing, where we are trying to focus on various thousand components requiring data transmission together, mass data integration, multimodal modeling, system-wide optimization. So this is not just simple engineering. It becomes system engineering at a global scale, a complex system, large scale integration. So as we move from bottom to upwards, complexity increases, data requirement increases, and the value of digital twin also increases. So now that we understood how digital twin works, let us look into the core areas where this digital twin is applicable in mechanical engineering. These are the four core areas, but not limited to. The first area is predictive maintenance, as I've been talking about it a lot, like various mechanical systems. This helps to avoid unpredicted breakdowns and reduce machine downtime. I will go through in detail in coming slides. Then product design. helps us to improve the design based on the real-time field testing of the model continuously. Manufacturing, uh, turning the regime into smart, optimized manufacturing, and structural health monitoring, where structures like bridges, aerospace components, and so on can be monitored continuously to enhance the safety and extend service life. These these are only a few examples, not complete broad spectrum applications of digital twin in mechanical engineering. So across many manufacturing systems, structural health monitoring is transforming how we analyze, predict, and optimize mechanical systems. This is the core area. Predictive maintenance and structural health monitoring is the core area when comes to digital twin in mechanical engineering. Then comes manufacturing and then product design. So let us quickly understand how digital twin enables predictive maintenance. Instead of waiting for the machine to fail, we now predict failure in advance. Digital twin combines real-time sensor data, physical physics-based models, and AI. This allows continuous monitoring of machine's health. First, the sensor collects the data, various data like vibration, temperature, speed, for example, of a bearing of a spindle. Then the data is fed to the digital system. This is already understood. Then the digital twin compares the actual sensor data with the expected behavior. If there is any deviation, for example, abnormal vibration pattern, then the anomaly is detected. Then we can schedule a maintenance period before the entire system shut down. Then once uh, after that, we can also predict the remaining useful life. So the digital twin detects its early and predicts failure in advance. So maintenance, planned maintenance can occur and it is not reactive. So the key benefits include early fault detection, reduced unplanned downtime, lower maintenance cost, increased equipment life. So machines are no longer waiting to fail. They tell us in advance. This is the major transformation in modern mechanical system when we take into the perspective of digital twin. Then the role of digital twin in product design optimization. So within the digital twin, design becomes a continuous data-driven process. Like uh, initially, we might have a design, we deploy it on the field, then collect the data in real time, like load, vibration, operating conditions. Then second, this data is cleaned and transmitted to the virtual model. Then third, the digital twin compares the real performance with the simulated behavior. If there is a mismatch, then it will give us other optimized design parameters. So we modify maybe geometry, materials, or parameters, and finally update the design. And this will be again virtually tested without deploying onto the field. So this is a cyclic process of continuously improving rather than we design, produce it, analyze it, and fix. We are changing the entire product design into design, monitor, learn, and improve continuously. So, for example, in a turbine blade, some sensors may have detect a higher thermal stress in certain region. Then digital twin identifies this and suggests design improvements like better cooling or improvement in material or enhance changing the geometry. So the key benefits include reduced prototyping development cost, faster design changes, improved product performance, and higher reliability. So the key line would be products in the field continuously improve their future design. So once we deploy a system or a design and it is in the field, we can improve its design continuously over the future designs. Now let us talk about how digital twin is transforming manufacturing. Instead of fixed manufacturing process, Manufacturing systems using digital twin are becoming adaptive and intelligent. So it allows real-time monitoring and optimization of manufacturing systems. So this connects machines, data, and intelligence into one system. So the working architecture is almost same. We get the data from the sensors and digital twin analyzes it. But what is it? How is it different from the previous? So the here instead of just analyzing and predicting the behavior, here in the digital or smart manufacturing system, the twin simulates the process and compares the actual performance then with the expected behavior. That is, it optimizes the process parameters. For example, take machining process like feed, depth of cut, tool generation or tool path generation, and so on. Then it detects potential failures and predicts maintenance needed. Finally, it sends the feedback to the machine to enable automatic adjustments. In advanced digital twin controlled machines, these adjustments can happen in real time. For example, in a CNC machine, if a tool wear increases, then digital twin detects it and adjusts the cutting parameters like reducing the spindle speed in real time so that the objective of surface finish is still intact. So the key benefits here include increased productivity, reduced downtime, improved quality, and enables autonomy or autonomous control. So we are moving a static and reactive manufacturing system to adaptive self-optimized system. That is, machines doesn't just operate; they learn, adapt in real time. Finally, we let us look at a digital twin structural health monitoring. So usually, what systems without digital twin do is they instead of they do periodic inspection, go onto the bridges, analyze the structure. But there might be a scenario where this will not be useful as it costs in crores and also lives. So instead of periodic inspection, structures can be monitored in real time continuously if you have a digital twin. That is, sensor collects the data such as vibrations, temperature, structural health, then send it to the digital or virtual replica of the system where it simulates the expected behavior using models like stress analysis, fatigue analysis. Then it compares the actual data with the predicted behavior to detect abnormalities. If there is an abnormality detected, then it will also tell us what will be the final useful life of the structure or give us a periodic maintenance schedule. So the maintenance can be planned before instead of having the structure failure. So the structures can now be continuously monitored and report their health and predict their future utilization. So the key advantages is early damage detection, improved safety, better maintenance, and extended structural life. So instead of just inspecting and repairing them, we are monitoring and continuously analyzing its health. So these are the four fundamental applications or core applications of digital twin. Then let us move on from applications to a real case study where my specialization comes from. So let us take a virtual case study of a virtual or a digital twin of a machining system. So most of the traditional industrial machining research in industries still involves only trial and error, leading to lot of higher cost and uncertainty. If we have a digital twin, we create a digital replica of the machining process, including various sensors like dynamometer, accelerometer, temperatures, and so on to continuously monitor the data, and the virtual replica can analyze it and give us the optimal parameters. That is
Sir,
like,
sir, I got some question here.
yeah,
So this is a sense. So for example, you got some routine production. So when the production is there, are we going to put the sensor? We are not going to put the sensors on each and every part that is being machined, right?
Yeah, that's a good question. So now people are moving from sensor-based data collection to inherent system-based data collection. Suppose you want to analyze a spindle or cutting force. You need not require a dynamometer now. Even spindle, if you're measuring spindle current from the control system or the architecture of the machine alone can give information of force. So that is what next my coming slides will explain. So let us continue. Okay. So this digital virtual machine virtual system can enable uh, or can process are helpful in reducing the tool wear, improving surface finish, reduced trial and error, increased productivity, and so on. But this requires a lot of data, and practical deployment is limited because pure data driven lacks physical interpretation at all. That is, the challenge is highly complex and requires high data requirement. So, if you really need to understand the system to overcome the failure of data driven models, we need to use physics based digital twin models. That is, uh, this model actually represents the mechanics of machining process. So something like this figure. So the mechanics of machining in a virtual scenario should fundamentally include the dynamics, that is structural dynamics of the system, the process itself, that is machining scenario, various control algorithms that are required to control the CNC machines, and the kinematics, how things are moving relative to each other. Let us take this example. So if you want to understand whether your cutting conditions would result in vibrations, how do you know it? So analyzing thousands of data, just cutting the material for a tool workpiece combination would not be helpful. If the material and tool change, it should not be, it becomes difficult and it requires a lot of data. In those cases, analyzing the system from structural dynamics point of view, analyzing how the cutting forces are generating the vibrations, not only using sensors, maybe using integrated systematic approach. To understand how really cutting force generate vibrations, we need to understand how force is generated. Then this force is generated from the process itself. So you need to understand how process is generating or predicting the force. Then this predicted force or the force generated during cutting will act as a external disturbance on the control algorithm. Then the control algorithm should be capable of adaptive and capable of developing control signals to adapt for the external disturbance generated by the cutting force. So this is all interactive dynamics process control. So this synergistic integration of all these components is necessary to predict the process variability. For example, take a simulated machining part of these components. Okay. Uh, so if you see, without understanding process physics, just using data, you see, this is the generated deflection tool path, and based on the generated commands like G codes and M codes of the tool path, if you analyze them in real time, you see this is how the tool deflection occurs, because this model is generated using only data without understanding the process physics of structural dynamics behind the machine tool operation. Now we have used a simple tool deflection compensation. Now you can see for the same tool path is not changing. I am only changing the parameters, that is feed, speed, depth of cut, with deflection compensation that is coming from structural dynamics. You see the tool path with deflection, tremendous improvement. So new sets of speed, feed, or cutting parameters will be developed. So while we provide deep understanding using physics-based model, but these might not be really suitable in real-time applications. So that is why we need hybrid digital twin models of machining. That is reduced order modelings of physics-based models combined with data-driven integration models or machine learning models. This allows to take the advantage of both the approaches. Physics-based models improve understandability and reliability, while data models provide adaptability and real-time learning. So as a result, this enables identifying root cause parameters, which requires very less data, and the decision is much faster. So it combines physics and data to make machine intelligent, efficient, and predictive. So in advanced system, this also enables adaptive control where the machine parameters are adjusted automatically without human interventions. This is the current scenario in advanced manufacturing systems in Taiwan and so on. Now, let we move. So we have talked a lot about digital twins in manufacturing application and so on, but there are very high stakes to implement digital twin. Key challenges, that is digital or data integration and management. That is, you have high volumes of data, breaking this data, labeling them, cleaning them, and making them ready is a uh, lot of process. Then computational cost. No, all industries cannot uh, comply or cannot comply for whatever computational costs are required because huge data has to be processed, and lot of efforts that are required to reduce the high fidelity models into reduced order models. Then the problems comes with model accuracy and drift. So many sensors will try to drift over the period of time, which require continuous calibration. And also physical systems, age, wear and tear, materials, and environmental uncertainties that has to be compensated for. Then interoperability, that is the connection between different communication protocols and softwares. Like I have a Siemens machine, there is another machine, then there are only few global protocols, communication protocols, that where we can send the data from between the two machines to exchange. So we need universal communication protocols. And the last one is cyber security, safeguarding your digital asset from attack, operational data privacy, intellectual property protection, and so on. So coming to the conclusions, digital twin is not just a simulation. It is real-time data-driven dynamic system which enables shift from reactive to predictive and autonomous system using physical system, data, models, and AI. The key impact on mechanical engineering includes predictive maintenance, product design and development and optimization, smart manufacturing, structural health manufacturing. Sorry, structural health monitoring. Future scope includes moving towards fully autonomous, self-learning, cognitive AI-based advanced systems, wider adoption in various sectors like energy, aerospace, automobile, and infrastructure, like the slide 7, which I predicted. Then, to conclude the entire lecture, digital twin is just not a tool. It is becoming the backbone of next generation mechanical systems. So these are some of the references. Thank you for your attention. I hope the session is useful.
Of course.
Yes, sir.
Session is basically fitting exactly into our main objective, main theme actually. You know,
Okay,
the
thank you.
title of our very faculty development program is Next Gen Mechanical Engineering.
Yeah, I try to correlate the lecture to that.
Your thing is correctly fitting into next generation mechanical engineering. So it's fortunate that you already started. You are getting prepared for it, and you are able to explain so many things about it. Okay, let me ask
Actually,
our.
some of my MTech students are working, integrating on this smart decision making, adding visions to mechanical systems and so on.
And small question, sir.
Please.
Yes, sir. Actually, this digital twins, is it applicable to a total system, or is it also applicable to components? So what I'm
So
trying to say is, if you take a turbine, if you take a full hydro generator or a turbine system, then what happens is you have so many components. Like if you take a thrust bearing, tilting pad thrust bearing also, see there's a lot of system-based tribology involved. So do you monitor the components, or do you monitor all the variables in the components, and also all the other variables in the system? But component is
yes,
that's what I'm trying to say.
strictly speaking, it is combination of observing multi-model components together to analyze a system level integration.
And learning,
So
machine
you
learning.
cannot simply say I'm modeling just a component. So if you model several components together, you are explicitly modeling the entire system. But deploy, as I told, if you go to my slide 7, wait, let me go. You see the level of integration. I can put G input. Right. So if you go to your question, you can say this is where you are asking. You can see the total system level digital twin deployment is less than 10%. Yet we have lot of scope to move into that region. Even though we talk theoretically, as I told, implementing them in real time has a lot of challenges. So moving from a component level to entire system level is highly challenging.
Okay. Sir, one more question. This is regarding about the how to teach this subject to our students, because Mm, oh, sorry. I am audible, sir.
Yeah, you
Hello.
were audible. Continue. I
Yeah,
thought
yeah.
you were
The thing
speaking
is
more.
that when we look at all these slides, and you are really a fantastic subject, and you are really doing extraordinary work in this field. I'm very happy, and I congratulate you also.
Thank you.
The thing is that how to teach the student is the one of the main issues coming over here, because it integrate so many systems, sensors, data capturing, modeling, again simulating, dynamic environment creation. Everything is there almost. Whatever
Frankly,
the things.
frankly speaking, I have experience with both Indian educational system and foreign education system that give me exposure to answer this question rightly. The fundamental drawback agreed by major academicians in India is that we don't teach mechatronics
Yeah.
from the basics in mechanical engineering. We see control systems to be a separate part of electronics. That is where we are lagging behind. We need to start integrating mechatronics from second year. Start teaching them simple data transmission, signal processing, analyzing them, so on. So without which we cannot teach this at a stretch in fourth year. So even though we teach, there are so many components involved which needs a lot of background understanding. So this is where I fight with the NIT also. I always complain that the syllabus curriculum
So,
needs to be improved a lot. So
mm,
the answer is to implement this step by step. Take each of the component like mechatronics in second year, integrate controls in third year, then go on to digital implementation of mechanical systems in fourth year. So it is a step by step or semester over semester. It has to be improved. So I don't believe this can be taught in a single semester thoroughly.
yeah, yeah. A series of subjects are involved over here,
Yeah.
and they have to be streamlined, like
Yes.
5 to 8 different electives, or even 10 electives. Like that, this is going to be for the student. But student need all these people, because now every plant becoming a smart manufacturing plant.
Yes. Yes. And
Obviously,
also
this
we
is
should make
knowledge definitely required.
And also, we should
Okay,
make
sir.
the students ready for the industrial environment, which is rapidly changing. After COVID, the pace at which the
Yeah.
industrial revolution occurring is out of our hands. So, if we don't implement
Right.
digital technology or digital twin based modeling or system analysis, then we are generating students where they don't fit into our industrial expectations.
Sir, for great information. We are very happy at what is digital twin. We thought of it is beyond our understanding. Okay, thank you, sir, for that.
Yeah, thank you very much for the opportunity. So, shall I end the session? No more questions?
No, we'll see. Are there any more questions? Participants, please.
Sir, one question, sir.
Yeah.
So what you're saying is that this digital twin technology is mainly used in process plants and areas. You cannot use it in for research, right?
No, how
So
come?
because it's
This
very,
is,
it's got to,
that is a complete converse statement. I mean, which objects the real foundation of digital twin. See, as I gave the
okay.
example, if you go to the machining example, so when we talk about only component or system level integration with data, it doesn't understand the physics behind. Right? Who is developing the physics here? We researchers, right? So the fundamental foundation of digital twin is the research or the physics based models or reduced order models that we contribute to enable the digital twin to make decisions. So we cannot say that okay, this can be applied only to the factories where they monitor and analyze. So still for our application, that is what I told, right? If you go to the slide 7, it is still, you cannot even say, strictly speaking, you cannot even see a smart CNC machine in India is the parameters in real time. I don't think so. In most sophisticated systems also, mostly in very various industries like chip manufacturing industries in Taiwan, they really implement this kind of technology today. Like some of my peers at UBC or I mean my professor, my supervisor, my team works on these digital integration and digital twin for manufacturing plants there. So this is the foundational step, so we cannot skip. So it is useful in research, and this forms the stepping stone for the digital twin.
Just, I mean, from the very primitive times, for example, 1970s, the computer simulation, sorry, finite element analysis was very strong from 1960s to 70s, and between 70s and 80s, commercial softwares have come. So that's how the simulation, whether they coupled multi-physics type of problems related to mechanical and metallurgical engineering, chemical engineering, have really flourished a lot. Now this is a different time that you want a system to simulate, and you want it to uh, optimize it, and predict it, and then it is going to adapt from the experience from the to update itself. So that is the intelligent system I am understanding.
In real time, that is the major difference.
Real time, real time. So many times you
So
said real time.
suppose we are trying to manufacture an aeroplane wing. So it is a single part. We don't assemble them. It is a big component. So some of the parameters are resulting in chatter, and you have everything. If chatter occurs, if the system surface deteriorates, surface integrated deteriorates, which will eventually result into residual stress formation and product failure. So people pay a lot of millions of dollars to
Correct.
make good surface finish without understanding the process dynamics. So if you understand the process dynamics, but solving that kind of process dynamic system takes few hours. So there we convert that physics-based system into reduced order model, where it can simulate the result in few seconds. So suppose it is moving from that location to other location within maybe 10 seconds or 20 seconds, the field, speed, depth of cut will automatically change. That is where the intelligent systems are coming. Future.
I have one thing. Suppose in this digital twin and all that, suppose the loading of the specimen workpiece into the CNC milling machine. Suppose if it is loaded wrongly, and this ideally vibration will not come. Suppose manually it is done, but it's all depends on the program how it is done. Okay, so there the chatter vibrations unnecessarily they are coming. So how it is going to take care? I mean,
So the source of vibration, as you told, that is once a mishandled equipment or a misplaced equipment, and the other is regenerative chatter. That is the cutting conditions are itself causing a regenerative chatter. That is cyclic loop of change of chip over a time using a delay period. That is the chip generated unevenly in this cycle is enhancing or changing the uncut chip thickness in the next coming cycle. Okay, that is one source. The other source, as you told, how the machine can understand this. So there are different signatures of vibration generating from chatter and also mishandled equipment. So chatter has particular frequency. If it is coming from regenerative chatter operating at cutting zone, mishandled workpiece has different vibration signature. That is how it can observe where the source of vibration coming from. The next is using a digital camera. So integrate a camera, it understands ideal setup with a, entangled setup or a disjoint setup. So it understands and it will give instruction to operator. There human interaction is definitely needed, or if not, the workpiece has to be picked up. Intelligent decision making. See, people want it also.
okay.
So there are different ways of analyzing where the source is coming from to really pinpoint the location of anomaly.
Yeah, I think this is definitely for the next generation of mechanical engineering,
Yes,
and
yes.
it's already you are into the thing, and so the other people they got to get into this thing. I think we got to listen to your more lectures if you are
Sure, sure.
keeping them in public domain.
Definitely.
would like to would like to
My professor Yusuf Altintas has approximately spent his uh, 33 decades of his research to develop digital twin of machining. So it's not that easy. So to completely understand from simple speed feed depth of cut to generate real-time process parameters, analyzing force, stress, tool wear, residual stress, everything. So that represents a process twin. So it is been integrated with Dassault systems. It might take some time.
but overall it has got a lot of opportunities in the sense, for example, steel making,
Yes, yes.
like and also in the Boeing aircraft also.
Yeah,
They
yeah.
got already some systems in place. For example, how many hours it has to fly and then replace it, inspect and again certify it and put it back. The crack length internal non-destructive testing, they do it and certify and all of they're taking care. That's why
Yeah.
all these aeroplanes are 100% foolproof and safe.
Yeah, yeah.
99%, right? Huh? Yeah, of course. Once in a while it happens. I mean, every
Yeah,
day
yeah. Definitely.
thousands of aeroplanes are going safely on the
Hmm.
road. Actually, many more number of people are
The
dying because of
anomaly might not be only from digital twin ignorance of human interaction, like human require some kind of input, may also cause or ignoring the warnings.
that.
Several things play a role.
Correct. So I say this kind of thing it has got a lot of opportunities in the in all kinds of fields like steel making or aircraft or even in military missiles and things, in the rockets and things like that. So I think if there are no questions, I really thank you profusely for taking your time and educating the participants. The faculty development program, we need ideally this kind of lectures in the future also. And
Okay, definitely. I will be- Okay, please. The thing is, I am starting from scratch. so, so I'm integrating various things together. Might take a leap, maybe some time to really have my own systems. I just started about an year ago here, so I require a lot of funding. I have a lab on my name, but we don't have a infrastructure. So we have a Siemens Center of Excellence for Digital Manufacturing in NIT Warangal, which we have basic things to work together, but someone's need to integrate them, right, to make them work. So we have all these things, but yeah, I am working on integration.
If there are no questions, I think we will close the session. Thank you.
Thank you for this
Dr. Naresh
opportunity.
Kumar.
Yeah, thank you for this opportunity.
Thank you. Welcome.